A third of the electricity in my house comes from nuclear power. That's how this sign is lighting up. There's a nuclear power plant down the road. It's making the electricity flow through this gas and it's lighting things up. You know what else is powering? These lights right here. Today on Smarter Every Day, we're gonna start something that I've been wanting to do for oh so very long. I just haven't done it because I've been a little nervous because I wanna get it right. We're gonna start the Smarter Every Day deep dive series into nuclear power. I wanna get this deep dive series right because when people hear the term nuclear, it's a loaded term. I mean, most people come to their awareness of the raw physical power of atomic energy through knowledge of atomic weaponry. We've rightfully been taught for years to fear these weapons.
What are you supposed to do when you see the flash? Duck and cover.
Tony knows the bomb can explode any time of the year, day or night. He is ready for it. Duck and cover. Attaboy, Tony. That flash means act fast.
So in order to do this right, I want to move from knowledge to understanding about how such an incredibly powerful thing can be harnessed safely for the good of humanity. So I think an appropriate place to start is the first place that ever happened. EBR-I, the world's first nuclear power plant. How did it work? We're going to figure that out today, and we're going to gain an understanding of nuclear power. That's what I want to do with this deep dive series. We're going to see people handling nuclear waste. We're going to meet this long-haired guy that's glass blowing to measure temperatures inside nuclear reactors. We're going to meet people that make this stuff happen, and they're interesting, and they're smart, and they're compelling, and I'm excited. So here we go. This is the first video of many of the nuclear power deep dive series here on Smarter Every Day. So make sure you're subscribed, maybe even sign up for the email list because these videos are incredible. I don't know if you know this, but there are 17 Department of Energy national labs all throughout the country here in America, and these places do all kinds of incredible research that's going to help us have a new clean power future, and I'm really excited about that. To get started, let's go to a very interesting place.
If you want to learn about nuclear reactors, the best place to do it is out here in the middle of Idaho at a place called Idaho National Laboratory. Let's go get smarter every day and learn about nuclear power.
So about an hour outside of Idaho Falls, Idaho, there's a building that was made in the 50s. This is the home of EBR-I, Experimental Breeder Reactor 1, and I went inside and met Andrew, who's going to show us all about how EBR-I worked. Okay, here we are at EBR-I, and this is Andrew.
Hello, folks.
You're going to walk us around, right?
Yeah, I suppose so. I'm not sure, did you have any specific questions for me? Do you want to just look around and take a look at everything?
Yes, I do. EBR. What does the EBR stand for?
So that's Experimental Breeder Reactor 1. We had breeder piles before this, but they weren't technically reactors. This is the first real breeder reactor.
What is a breeder reactor? What does that mean?
Ultimately, a breeder reactor is taking uranium-238, bombarding it with fast neutrons to produce plutonium-239.
Okay, don't freak out. I know that was a lot of words, but we are totally going to understand what he just said.
It's best to start upstairs.
Let's do it. I'm following you. This
All
looks
right.
awesome, by the way.
I mean, this place was built in 2 years, which is truly incredible. I always joke with people who come through that I'm not sure that we could build a shed in 2 years nowadays, let alone a whole reactor.
Oh, by the way, I just went to the restroom a minute ago, and it just looks cool because you can, I'm sorry, I'm gonna do this. Look, you can like see like all of Idaho wilderness out there. It looks awesome. It's just a cool place. So the fonts are great. I love it.
I think we'll probably start in here just to get a bit of a rundown of things.
All right.
So this diagram helps me explain breeding just a little bit. There are two isotopes of uranium that occur naturally, 235 and 238. Uranium-235 is what's useful to us in a reactor. That's an unstable atom. We can break it apart and harness the energy from that breaking. Unfortunately, 99.3% of uranium is 238, which is too stable to be split, but you can use it to make plutonium. So what you have to do is separate the 235 from the 238 until you've got a concentrated amount, and then you can build a breeder reactor.
Now, so you're breeding plutonium, so you're
Yes, sir.
making plutonium, and that's what's actually giving you ultimately the electricity.
Not in this case. So the uranium-235 is kind of running double duty. It splits. In the process of splitting, some of that mass is transformed directly into heat. That's what we're going to use to make electricity, kind of like a coal burning plant.
Yeah.
But it also releases neutrons, and we can use the excess fast neutrons that aren't needed for splitting extra uranium to breed plutonium.
Nuclear power is intimidating for people to understand, myself included. So as a result of that, I have spent a lot of time with flannel and googly eyes and 3D printing some stuff, and we're going to take a stab at understanding this. Okay, so Andrew said there are two things going on at EBR-I. He said there's heating, and he also said there's breeding. These are two separate things. Heating is how we make the electricity, so let's focus on that right now. We'll talk about breeding later. So how does a nuclear power plant, in this case EBR-I, make heat? Let's start with a very important atom. It's uranium-235, and in this little example here, all the protons are red and the neutrons are blue. I want to introduce you to our hero. This is a fast neutron, and when you see this fast neutron, I want you to think of this. Wee, wee, wee. It's so silly, but this is what makes nuclear power possible. So we've got this fast neutron, wee, hitting uranium-235. Now, one thing to remember about uranium-235 is it's about 0.7% of all the uranium in the environment. The rest of it, 99.3%, those are all different isotopes of uranium. So when this fast neutron hits uranium-235, it's not like a billiard ball ballistically like blowing up all the protons and neutrons. It's a different thing. It fundamentally changes the nature of this atom, and it's no longer uranium-235, it turns into uranium-236. Now I've got these different color googly eyes to represent the fact that uranium-236 is a little bit different. It's spicy. So uranium-236, really deep on the periodic table, there's a lot of forces at work. It doesn't want to hold itself together. It's not as stable as uranium-235. So this exists for a very short amount of time, and then something interesting happens. It actually splits. This is fission. It splits the atom into two new atoms. This is not a chemical reaction. This is fission. We are splitting that atom into two new atoms, and they're very surprised to exist. Of course, they are different atoms. We've got krypton and we've got barium. Okay, so these new atoms exist, but the act of splitting that atom has a byproduct that's very, very important, and that is heat. So I'm going to add heat to the board here. So we've created two new atoms, and we've created all this heat, and if we're clever, we can use that heat to create electricity. But there's another thing that happens as well, and it's going to take me just a second to get all my heat on the board here. So we've got these new atoms, we've got all this heat, but there's something else that happens. We actually create three new fast neutrons, or I guess they kick off of the fission. So you've got these fast neutrons going off into space. Wee, wee, wee! They're just flying off. So everything you see on the board here was in that uranium-235 atom when it was hit by one fast neutron. So if you think about it, we can think of that uranium-235 atom almost like a spring-loaded mousetrap. It's got potential energy and it's stored up, and it's even got these three extra fast neutrons over here. And when you hit it, it'll spring off and it'll do crazy things. So if we think about that, and then we cleverly arrange a bunch more uranium-235 atoms out here around that initial fission event, then we can do a really cool thing. With that fast neutron that's kicking off the splitting of the atom, it can go over here, and if there's another U-235 atom in the proximity, it can slap it and trigger it, and then you create this whole thing all over again, creating heat and three more fast neutrons. So by cleverly arranging U-235 atoms around each other, scientists and engineers can create more fast neutrons from one fast neutron triggering a U-235 atom. It's almost like a bunch of mousetraps ready to go, and if you cleverly arrange them, you can create heat at the rate that you want. So by controlling the proximity or the probability of the interaction of these fast neutrons with these other U-235 atoms, scientists and engineers can control how much heat is created in the reactor, which is amazing. We're going to learn more from Andrew as we learn more about the plant, but I have some more felt stuff later that has electric motors attached to the board, and I think you're going to enjoy that.
What's your deal, Andrew? Are you a student? What's your deal, man? I gotta know.
So I'm a mechanical engineering student.
Yeah, you
I just have a deep love of history, so I wanted to work out here, get some public outreach before I'm stuck behind a desk.
You're not going to be stuck behind a desk being a mechanical engineer. You're going to be building awesome things, man, like reactors.
That's true. I'm more meant just, I get to talk to people and interface with the public while I'm out here because there's so many misconceptions around this technology and its safety, but this is the first reactor ever really made to produce electricity, and it has a bunch of inbuilt safety features that most people wouldn't have even expected.
Is this how EBR-I worked?
Yeah, essentially.
So the reactor, and then that's liquid going through there.
Yeah, it's a liquid metal. It's a bit unique compared to most modern designs. We used a mixture of sodium and potassium. It's a liquid metal eutectic, which means if you get the right alloy, it has a lower melting point than either of the base elements. In this case, like mercury, it's liquid at room temperature. They had to use a liquid metal because water absorbs and slows down neutrons, and they needed fast neutrons to produce plutonium. So they had to find a way to make the liquid metal work, and that's why the system looks a bit weird. Technically,
yeah, it usually goes like from here to here.
Yep.
Yeah, and you don't have this loop right here.
And technically, to make this function, you wouldn't even need this middle loop, but it's there for a pretty good reason. If you were ever to have a breach between these two pipe systems that allowed the two coolants to mix, you'd get a pretty big explosion. The alkaline liquid metal will basically rip the hydrogen off the oxygen in the H2O, so you do get an explosive reaction. They would not want that to be highly radioactive. So by splitting up the liquid metal loops this way, the highly radioactive coolant is sequestered in this first loop. That provides one level of safety. There's a second level that exists in the secondary heat exchanger. We'll talk about that downstairs.
All right, Andrew did a great job of explaining everything, but selfishly, I just wanted to build it and play with it to understand it better. So that's what we're gonna do. The first thing I wanna talk about is the fact that they use liquid metal. That's a pretty big deal. So I purchased some gallium, which is a room temperature liquid metal that you can just buy and play with. It's really fun to see a metal flow like a liquid. But why did they do that? That's a really strange design choice. So the fast neutrons, when they kick off of a uranium-235 atom, those things are going 14,000 kilometers per second. Very, very fast. The thing about fast neutrons is when they go through water, they slow down. So if you have just water like this, there's a bunch of hydrogen atoms in there, and that fast neutron will interact with them, and it'll slow down to 2 kilometers per second. That's not good if you want to use this as a breeder reactor, which is what they wanted to do. So there's this other material called NaC, sodium and potassium. You can see how it gets its name right here, Na for sodium, K for potassium. NaC is not a moderator like that. So the fast neutrons will just zip through this. And it's also a really good conductor of heat. So it makes an ideal liquid to transfer heat away from the reactor. So the first two loops in EBR-I were NaC, and the third loop was water. Now, just like Andrew said, that first loop is isolated from the second loop so that if you did have NaC come in contact with water, because that doesn't work well, it'll explode if that happens. If you have an explosion, you don't want it to be a radioactive explosion. So you isolate all the radioactive stuff over here in loop 1, and then, well, let's just see, how do we get heat from the reactor all the way over there? So let's look inside of our loops here. You can see there's our reactor. That's just a heat exchanger. That's a heat exchanger with some steam in it. Okay, so let's look at how this works. So I've got this little setup here. I've got a little distribution panel, so I can turn things on and off. I've got a bunch of motors and stuff behind the board there. I'm gonna show you how this works. So first of all, let's turn our reactor on. I'm gonna take this and move it up, and we'll understand why that turns the reactor on later. So our reactor is now running, and we are creating heat inside the reactor. The problem is if we just keep making heat over and over and over and never do anything with it, it'll just sit there and melt everything down. So we have to move the heat away from the reactor, and the way we do that is with NaC. So we're gonna turn this little pump on here, and we're gonna pump NaC through the system through this heat exchanger. So that gets us to the second loop. So the interface between loop 1 and loop 2 is basically a pipe within a pipe. That's a heat exchanger. So they're mechanically isolated from a fluid perspective, but they're not thermally isolated. They're actually thermally coupled. Pipe within a pipe, that's a heat exchanger. And once we get here, we can just simply turn on another pump here, and we can pump the heat over to the third loop. Now, the third loop is important because we have water in there, and when you heat up water past a certain point, as you know, you make steam. That steam can be converted to mechanical power. So we're gonna take
thermal power, move it all the way down, and convert it to mechanical power by activating this turbine right here. So at that point right there, we can use that to turn a generator and all kinds of things like that. And as the steam goes through the turbine, it loses energy, and we can condense it back into water, and we can send it back into the loop. We can just use this loop right here over and over and over. And if we hook a generator up right there, we can actually create electricity. So that's what we're gonna do right now. Let's hook up our, let's just hook up those wires, and there we have it, light. We have done it. We have created the world's first nuclear power plant. We've gone from nuclear power, thermal energy, all the way to electricity. This is the world's first nuclear power plant, EBR-I. And remember, this is a fast reactor. There's two types of reactors, a fast reactor, which uses fast neutrons, or a thermal reactor, which uses a moderator, which slows down the neutrons. That's not what EBR-I was. And the reason they wanted a fast reactor is because of the breeding process, which we'll learn more about later from Andrew. But now that we know how all this works, let's go learn how they controlled it.
All right, let's take a look at the control room next.
I love your tour style, Andrew. It's great. You've refined it, haven't you?
Yeah, I've had a bit of practice out here.
All right. Is this control room?
Yep, this is the control room.
Is this where originally, this is the original control room?
Yeah, essentially everything in here is original. There are a couple of pipe systems I've noticed throughout the building that changed as they updated the reactor core, but that's basically it. Everything else is in the position it had started in the 50s.
So primary coolant was metal.
Yep.
Right? All this. These are measuring the temperature.
And I love these paper graphs. They measure time radially, so 24 hours is a full circle, and amplitude is measured from inside out. It's so simple and beautiful, and it makes perfect sense if they had to switch these out every day.
Yeah. Do you have any of the old blanks?
I don't know if we do or not. I'm sure that they exist somewhere, but I don't have access to them.
Okay, so here is an actual drawing. Yeah, you can see it. It's pretty cool. Oh, midnight right there. Midnight. So what time is it right now? It is 2:30-ish. So midnight would go 2:30. So right here, that is the temperature at that time. I just don't know how to measure it. Okay.
Yeah, they're a bit hard to read, but there is something really nice about these old systems. I've had some old nukes come through, and they tell me that with this sort of very analog way of recording data, it can be really intuitive for the human brain, because you can look at the circle and see what portions of the data are larger or smaller as far as amplitude goes and read it very quickly. In a modern digital system, you'll have maybe a catalog of 10,000 entries for whatever the amplitude is you're recording.
Yeah.
And oftentimes, that's harder to understand for the human brain than looking at something like this. You can pick trends out a lot quicker with this.
Okay, this is unrelated to nuclear power, but I think you'll enjoy it. So I am working on my PhD, and as a part of the PhD, I'm trying to do what's called modeling and simulation of an event that I did back in the day. Two objects clashing together at a very high rate of speed. It's really fascinating. But what I'm trying to do is I'm trying to create a digital version of that event, and then I'm going to do what's called finite element analysis. Basically, I take the objects and I divide them up into little finite elements, and then when you do that, you can calculate the forces going in one of the triangles and then the forces going out, except it's in three-dimensional space, and then you can use that data to go back and you can measure, with math, you can measure the stress all along the impact surface of these objects. Now, I'm doing this on a computer, which I want to go show you now, so let's go in there and check that out. Okay, this is my workstation. It's a special computer made by Puget Systems to run very complicated software. This is a piece of software called LS-DYNA. Actually, this is ANSYS, and I'm running LS-DYNA simulation on it. Now, the thing is, I can only run this simulation on this machine, and it takes a really long time to run the math. So today's sponsor is AnyDesk, which is remote desktop software for your computer, and you can check it out at anydesk.com/smarter. AnyDesk is fantastic and easy to use software that lets you remotely control computers. You can do it from a laptop or you can do it from your phone. So recently I had to travel up to the Northeast, and while I was there, every chance I got, I wanted to check in on my simulation to see how it was doing. On this train, I can tether with my phone and I can remote into my workstation back at home and I can check on the simulation to see how it's running. I love it. AnyDesk has changed my life.
I think there's something to be said for studying in a really cool room or doing some work in a really cool place, which is why I'm here at the New York Public Library.
I'm able to run my workstation from a remote location and work on my PhD in a really cool room. And I know that sounds dumb, but it's really cool and I enjoy it. So you should check out AnyDesk. In fact, the screen capture that you're looking at on the screen right now, I uploaded that back to my workstation back home using AnyDesk. There's a file sharing system built into AnyDesk. I love AnyDesk. It's seamless, easy to use, and it lets me do complex stuff like this remotely. AnyDesk.com/smarter. It's free, and the way they make money is they assume you're gonna love their software so much that you're gonna convince your employer to get a business license for the software, and I think you're gonna like it because it enables you to get your time back and operate more efficiently. Check it out, AnyDesk.com/smarter. That's the data. Looks pretty cool. Thanks for considering. This is amazing. This is incredible. Oh God. So they like hand calibrated.
And you'll see these notes all throughout the facility. Basically every system they were learning for the first time. So as they figured out how to do it, they'd write notes so that the next person to do it basically had a baseline to work from.
So this is incredible. So what they're doing is they're calibrating. So they have an analog measurement here and tank level in inches. And so this is the curve. And so this is how to read this. So if I said I've got 2 amps, I would say 2 amps. Oh, that is 35 inches is how much fuel is in my tank or whatever this is in your tank. Primary drain tank. Okay. I appreciate this so much. I used to do instrumentation, and one of the first things we would do is we have to make the curve for your instrument. And you kind of set the low end and the high end, and then you figure out how it all works. I've never seen that technique, and it's awesome. I'm sorry. That was a little too much geeking out there, Andrew.
Oh, believe me, I'm all for it.
Okay, that's awesome.
So then there's one particularly important button I always like to talk about, and that is, of course, the scram button. If I pressed this while the reactor was operational, it would be shut down in about 4 seconds. From the beginning of these reactor designs, they knew they had to be shut down quickly if the power was rising quicker than they could really ameliorate it in another sense. This system has 2 different ways of scramming. One of them would insert the control rods all the way in, it would slow it down over time, and then it was ready to start up immediately. The other scram system, which was I think pulled from this pulley here, would drop the outside blanket, immediately decreasing the reactivity to 0, and that would shut it down immediately. The only problem is they could not start back up quickly. They'd have to go through a process of making sure the blanket was good to go. Took about an hour before they could fully restart it.
So that's a serious scram.
Yep.
So this is the more graceful scram, and then this is the oh heck. Let's grab that ring and pull it.
And it used to hang down a lot further, but kids thought it was fun to swing on, so.
Oh yes, it goes up. Oh, that's interesting. And so it's in the middle of the room, so anybody can pull it.
Yep.
Okay. I could spend too much time in here, so should we go to the next place? Time to talk about breeding. Now, breeding is a very special thing. We can make nuclear fuel from nuclear fuel, and it starts with a uranium-238 atom. You remember when we were talking about uranium-235, this is about 0.7% of all the uranium you'll find in the world, whereas uranium-238 is more prevalent. It's about 99.3%. Now, when we did the fission thing earlier, and we kicked off, these little fast neutrons, when a fast neutron comes in contact, with uranium-238, that creates uranium-239. You can tell from his eyes that he's just a little bit spicy, right? So the uranium-239 exists for a while, but then about 23 minutes later, give or take, we have a really interesting thing that happens. We kick off an electron, and we have this process called beta decay that happens inside the atom. Some neutrons and and protons, they'd switch roles. It's kind of strange. And then we end up creating, as a result of this beta decay, Neptunium-239. Completely different element. You can tell he's very different. So after this time, we have another beta decay event. That beta decay event happens around 2 to 3 days later. We kick off one more electron. We have some stuff happen in the nucleus again. And then we create the ultimate spicy element, which is plutonium-239 that comes into existence. Now, the thing about this process is you're making nuclear fuel from nuclear fuel. And in fact, you can make more atoms of plutonium-239 than you put in to begin with of uranium-235, which is a very special trait for a nuclear reactor to have. In order to do all this, you have to get a fast neutron to hit the nucleus of a U-238 atom so it becomes U-239, but that doesn't happen all the time. Sometimes these fast neutrons bounce off, and the engineers and scientists that designed EBR-I used that to actually run the reactor. It was pretty interesting what they did.
Let's head out this door and see the reactor itself.
What?
Very close by.
This is it?
Yep. It doesn't look like much, but this is a relatively small reactor. So right now we're standing on the radiation shield for the reactor. I would call it a containment vessel, but technically they're a bit different. Containment vessels are essentially meant to hold in the products if they have a meltdown. This is just a big radiation shield. Normally there'd also be a big plug right here that would prevent radiation from coming out of the core, but now that it's been decommissioned, they can safely take that plug out and let us look inside. The core itself is just below that machinery. We'd feed fuel rods into it through that machinery, and the core is set up using these hexagonal assemblies. The center 7 contain the uranium-235 that's propagating the chain reaction, while the outside ring of hexagonal assemblies contains 238 to breed plutonium. There's not uranium in all 10 feet of these rods. It's only in the 8.5-inch heat zone near the bottom, about a football-sized zone. That's where all that reaction would take place. For this particular reactor, they operated using about 60 kilograms of fuel, and that means that there wasn't enough for it to go critical by itself. That's why this outside breeding blanket was necessary. It acted as essentially a reflector. It's made of 84 bricks of uranium-238. They're set up in this cup shape on an elevator just below the reactor core. The hydraulic elevator would bring that up around the core when it was ready to turn on. It'll reflect neutrons back inside and give you enough neutron flux for the reaction to occur. So we didn't use control rods for startup and shutdown. We used this for startup and shutdown.
That blanket. Okay, remember our board with all the stuff on it? I'm gonna put you on this tripod right here so we can look at how to start up and shut down the reactor. All right, so let's check it out. So as we raise the blanket, we start the nuclear reaction, and to stop the reaction, we just drop the blanket. That's how this works. So we have a physical control now for nuclear power, and that's how they came up with that. And to explain what exactly is going on there, I'm gonna have to change out the board to the other board. So let me do that now. Okay, let's build the reactor from the top down. So over here on the right, this is the top down view of the reactor. The red is U-235 enriched. The outside is U-238, okay? Over here, we've got the U-235 atom and the U-238. So this is like the conceptual model. This is the top down view of the reactor. So let's look at how this works. So when we get a fission event from U-235, we're kicking off those 3 neutrons, right? Those 3 fast neutrons. Wee! They're flying out here. They're going really fast, right? Sometimes they will interact with the U-238 and you might get breeding. So that, if you look at it over here, that would be leaving U-235 and interacting with the U-238 atoms out here in this inner blanket, they call it, right? So when it does that, sometimes it'll create plutonium. Sometimes it'll bounce it back into the U-235 to sustain the fission reaction. However, because of the arrangement, sometimes these neutrons, they don't hit anything and they just keep going. That's what the blanket is for. If we were to put a neutron mirror, let's think about it like that right there, and on the top down view like that, then this is what happens. So if the fast neutron flies, it misses the U-238 and it keeps going and it hits this big wall of U-238 atoms, right? These bricks of U-238. It hits this wall, it reflects then it will bounce back, and that increases the statistical probability that it's going to hit a U-235 atom. So your chances of sustaining a fission reaction goes way up because you're getting 2 shots with those neutrons, right? Well, maybe not 2 because some of them just keep going, but you get the idea. So it leaves the inner core, it goes past the inner breeding blanket, which is cooled by liquid metal, NaC, if you recall, and then it goes out to the outer breeding blanket, and then it sometimes will bounce back into the core. That's why applying, like if I did this, then it's very unlikely that it's going to bounce back. But if I did this, then we're going to bounce neutrons back into the core. That's why raising and lowering the breeding blanket is so important, and that's why they could turn on and off the reaction. If they balance the amount of U-238 and where it is and how many neutrons can go where, they can just flip a switch and turn on or off the reactor, which is fascinating. So that would come up and down?
Yep. Originally, they had it set up so it could only be fully up or fully down, but they realized that that wasn't ideal, so they added in some hydraulic control systems so you can get more fine tuning. And this is also where our control rods would go into. So we did have 8 control rods, but they'd go into the outside blanket for fine tuning. As the reactivity of these rods decreases over the 9-month lifespan, they'd pull the control rods so they could get the same power out.
So the outer blanket would move up and down?
Yes, sir.
And if it comes up, what happens?
If you bring it up, it'll increase reactivity until eventually you reach criticality and the reaction starts.
Because it's reflecting neutrons back in towards the fuel.
Yep. And this is also breeding plutonium. That's why it was made of uranium-238.
Okay. So you have to lift it in order for it to activate, and so gravity is your friend.
Yep, and that's why our scram system works in an incredibly simple way. When they scram this facility, rather than dropping control rods into the core, which is how it works for almost all modern facilities, it'll empty the hydraulic systems that hold the breeding blanket up and drop that down into the basement.
So it just opens a valve?
Yep.
Okay.
And that would shut it down in about 4 seconds, but it would take an hour to restart if they scrammed it that way. That's why they had 2 separate scram systems.
Are these actual fuel rod assemblies?
I think these are just mock-up assemblies and rods, but they are all exactly the size of the originals.
That's cool. And there was fluid in there, I'm assuming. Was there water?
Not water. So this would be the liquid metal cool part of the system. Right up here on top under the plug, there would be a layer of argon gas. That would prevent oxygen from ever getting down into the coolant. It could ignite the coolant if it comes into contact with air due to the oxygen. So this would be filled with argon, and there's argon in a couple of our other systems that we'll see as well.
Is argon heavier than air?
Yeah, I believe so. And for the case of argon, it acts essentially as a noble gas that's completely non-reactive. That way you won't have anything reactive come into contact with the coolant.
That's awesome. That's cool. Where to now, Andrew?
All right, let's go take a look at the generator where they powered the first light bulbs to ever be powered using nuclear energy.
Look at this. That's not actually true right now, is it?
Not anymore.
So that was true at the time, though, right?
Yeah, and it was also a huge point of pride to the men working here. It's important to remember that they had just come from the Manhattan Project, meaning their work had recently been used in Japan to kill thousands of civilians at Hiroshima and Nagasaki. Whether or not it was the right choice to drop that bomb is not something that I ever pretend to know or tell people. That's not really something I can decide because I wasn't there at the time.
Come on, Andrew, I'm putting all of that on you.
But really, they cared about producing power. They knew this could be an energy future for the world, and it mattered to them that they were on the other side of that coin. That sign was a point of pride because of that. From what I understand, they would never turn that sign on unless the reactor was producing electricity, and they would shut that off before they shut the reactor down every night. They really did care about that being true.
They cared about it. That's awesome. It was almost like plowshares. You're familiar with the verse in the Bible, beating their swords into plowshares? Have you heard of that?
Swords to plowshares.
Yeah, the Plowshares Project. And so, that was a whole different thing for people. That's great.
All right, next we'll head out to the generator. So a reactor only has one job. In the case of EBR-I, it's got 2 to produce both heat and plutonium. Through our heat exchange system, we boil water, we send the superheated steam up through the back of this turbine to spin it up, then through this gearbox, the generator is spun up even faster to produce electricity.
This is the gearbox?
Yes, sir.
Okay.
On the 20th of December, 1951, for the first time, they had all their systems in place. They had been turning on the reactor since about August, but they were finally ready to make electricity. On that first day, Dr. Walter Zinn, the lead for the project, wanted to start small, so he just strung up 4 300-watt light bulbs, connected those to the generator, and when they turned the reactor on for the first time to produce electricity using uranium for the first time, they just powered on 4 light bulbs. The next day, they connected it to the rest of the facility, and it would power the whole building going forward.
That's amazing, but this was the moment.
Yep.
Is this a photo of the moment?
Yep.
Really?
Afterwards, Reed Cameron thought that they needed to commemorate the occasion, so he got out a ladder and some chalk. He wrote this excerpt up on the wall, and everybody signed their names underneath it to commemorate the event.
That's the original?
Yep. They encased it pretty soon after they signed.
Electricity was first generated here from atomic energy on December 20th, 1951. On December 21st, 1951, all of the electrical power in the building was supplied from atomic energy. Those present, and those are all the people that participated.
Mm-hmm. Jolly signed a few days later. He was the local janitor.
Jolly did?
Yep, that's the name on the bottom there. But I think everybody else signed that first day.
So that is a moment. What is the picture?
So Reed thought it looked kind of boring, so he got back up there, he drew the character blowing air on top. Nobody knows exactly what it is, but literature and some of the memoirs from the men who worked here is that they figure it's the devil blowing air, creating energy. And personally, it kind of seems like their way of saying this thing that's been used as a horrible weapon can also be used to create power. But I can't attribute that to anything in specific. That's more of a me thing.
That's awesome. So this would have been powered with water. So where are the heat exchangers that take the heat out of the liquid metal and turn it into water?
We'll see those next. They're right below us.
Okay, let's do it. You guys are filling up. A lot of people visiting.
Yep, it gets pretty busy around this time normally.
Does it really?
So through this door here is the secondary heat exchanger. It might seem like an awfully big system for 45 kilowatts worth of electricity, but that's because it's a safe design, not a spatially efficient design. It's a pipe within a pipe heat exchanger. The innermost pipe carries the liquid metal coolant from the middleman loop. Around that is a pipe filled with argon gas, the totally noble non-reactive gas we talked about before. Then around that is the pipe carrying water to be heated, boiled, and sent up to the turbines.
So the heat has to go through the argon?
Yep. That's why it's so big, because argon's not particularly conductive. But the argon's there for a good reason. If you do have a pipe breach on either side, you don't want the coolants to come into to mix. That will cause an explosion. So instead, they'll only be able to mix with argon, which is completely non-reactive. That's why you have the jacket between those two layers. So I always stop here just for a moment. There's not too much to see in here, but this is the primary coolant loop feeding coolant right from the reactor. And I do like to note the thickness of this wall. A lot of people have the misconception that these early nuclear scientists would have received high doses of radiation working at these plants. That was true for some experiments that they operated, but not for the plant itself. This wall is 4 feet thick to act as gamma radiation shielding. They knew, based on studies they've been doing in Japan, that they had to shield from that radiation, and you need a minimum of 4 feet of water or high-density concrete or 3 feet of lead to mitigate those effects. That's why this wall is so thick.
And that's concrete. Oh yeah, those are not concrete. Excuse me, those are not cinder block bricks, they're concrete bricks.
Yep.
Okay.
So this right to my left is the cask that would allow us to pull spent fuel rods out of the reactor. It's a lead-lined container that helps trap the radiation within. The tank on the back of it fills it with argon so that when they pull the fuel rods, there's no oxygen interacting with the liquid metal coolant. They'd have to pull it one rod at a time, so it was a pretty lengthy process.
So they would put something down in there, grab a rod and pull it out?
Yeah, so basically they'd take this 10-ton crane above us in the corner, they'd hoist this cask up on top of the reactor, and it would sit on this plug, but this would be upstairs where the hole in the reactor we saw is.
Which is right up there.
They'd be able to rotate this plug, and then through these 3 hatches, they could gain access to the different parts of the reactor and pull just a single rod out at a time.
That's cool.
Once they have the single rod out, they'd close up the top of the reactor, close up the bottom of the cask, and move the whole cask for cleaning and storage.
And so they could just store the rods?
They had to store the rods. The daughter products within them, when you take this big atom of uranium and break it in half, those 2 daughter products are unstable. When they break down, they don't just release radiation, they also release heat, so the rods keep themselves hot for a long time. So you have to store them before you can ever do work on them. That way they have time to cool.
Oh wow. So there's a lot of thermal capacity there.
Oh yeah.
Fuel rods? Is this where they would store them?
This is where they would store the fuel rods before they went into the reactor. So the vault here might make it seem like you needed a bunch of shielding. Really, the vault's just to prevent anybody from gaining access if they're not supposed to, and for accountability. At the time, we were shipping all of our uranium from Africa. The military wasn't certain that we'd be able to continue those shipments, so they kept very tight track of essentially every ounce of uranium. We'd bring it here from Hanford, we'd weigh it before it went into the vault. If we ever needed, let's say, 3 pounds of replacement fuel, we'd have to weigh it very carefully before we took it out of the vault. So this kind of helps us keep track of all the uranium that we're using.
But they could just store the actual rods out in the open like that?
Yeah, you don't need any special shielding for natural uranium. This is concentrated 235, so it's not natural in the sense that it's pulled right out of the ground, but this hasn't started fissioning, which means almost all the radiation it produces is in the form of alpha particles, which will be stopped by your skin. You'd have to breathe this uranium in or swallow it for it to cause you cancer, and at that point you've got other issues because it's a heavy toxic metal. It's pretty benign in this form. The reason you have to be so much more careful once we pull it out of the reactor is because of those daughter products. When you take that big atom and split it in half, its instability will cause it to release radiation as it breaks down. That's the more dangerous form of radiation we have to be careful about.
Andrew, have you memorized this, or are you just shooting from the hip right now?
A bit of both. It's
Really?
not my exact tour schedule, but
But you actually know this stuff,
yeah.
and you love it.
Oh, of course.
Okay, great. That's awesome. All right. Okay.
I mean, this facility really is the perfect mixture of engineering and history for me, my 2 biggest passions, so I love this place.
It's awesome, dude.
Andrew really is a remarkable tour guide, and he showed me a ton of more fascinating stuff. And I'm gonna put that over on Smarter Everyday too, because I don't want this video to be an hour long. For example, he explained to me that EBR-I had a partial meltdown one time, but they knew this could happen, and they were testing the safety systems so that they could roll that forward into future reactor design. They used this event to learn about how to clean up after something like this occurs, which they clearly did because I'm standing in the facility. He took me downstairs and he showed me where they worked on the rods and the blanket to inspect them and repair them. They had to build impressive machinery to move these things around while they're radioactive, reactor parts. It's fascinating stuff. He also took me outside and showed me these 2 reactors. These were intended to be part of a jet airplane. The government ended up abandoning that program, which is probably the right idea, but it's pretty awesome, and I'm gonna put that all over on Smarter Everyday too, so please check out that video. I'm really grateful to Andrew for sharing his passion with me. This was a lot of fun. I hope you are half as excited as I am about the nuclear power deep dive series, because I've wanted to understand nuclear power forever, and we're finally getting to do it. So this is what I'm gonna ask. Typically, I would say there's a lot of videos here. Please consider subscribing to Smarter Everyday, but I don't think that works like it used to on YouTube. So what I'm gonna ask is, would you consider signing up for Smarter Everyday email updates? You can do that at the link down in the video description, smartereveryday.com/email list or something like that. If you would consider that, I would greatly appreciate it. I will notify you when a new video from the Nuclear Power Deep Dive series comes out. These videos are incredible. We filmed them at Idaho National Labs, but there's all kinds of stuff. We're looking at this special glass blowing thing. How do you measure the temperature of a reactor? What happens when you have waste that you have to handle? How do you do that? These are really, really neat videos, and I think you're gonna love them. So go check that out. So yeah, that's it. Please consider subscribing to Smarter Everyday via the email list, and a big thank you to everybody that supports Smarter Everyday on Patreon. I'm trying to make intelligent, respectful content that I think should exist on the internet, so please consider that as well down in the link. Last thing, I've got a link below to a form. If you have access to a currently working nuclear power plant, I'm trying to get into one, and that's proving to be difficult. And also, if you have other things in the nuclear industry you think I should consider, then there's a form down in the video description. If you'd click that and fill that out, I would really appreciate that. Anyway, that's it. I'm Destin. You're getting smarter every day. Nuclear power. Let's do it. Have a good one.